Well, so let us solve one question from CSIR NET 2018 June, and this is basically from nuclear physics. So in that question, it is given that you have a copper nucleus having atomic number 29, mass number 63. It is capturing a proton and is converting to zinc nucleus having atomic number 30, mass number 63 with addition of neutron particle. And this zinc nuclei is immediately decaying to copper having atomic number 29, mass number 63 with addition of beta plus particle, and you have a additional particle that is neutrino. So this is basically beta plus emission. The maximum energy carried out by this beta plus particle is given. That is 2.4 mega electron volts. In fact, it is given that the mass of a electron that is given as 0.5 mega electron volt per c square. Mass of a proton is given as 938 MeV per c square. And mass of a neutron is given as 939.5 MeV per c square. So what you have to calculate? You have to calculate the Q value of this original nuclear reaction. The important point here is given that the maximum energy carried out by beta plus particle. Okay, so you know that spectrum of beta plus particle is like this. This side you have a energy, and this side you have a number of beta plus particle or number of emitted beta plus particle. If you see that spectrum, it's like a continuous spectrum. It can have many possible energy, but maximum emitted beta particle having energy is E naught by 3, where E naught is the maximum energy of emitted beta particle. And this maximum energy, this number of particle here, the maximum energy carried out by beta plus particle will be less, but that maximum energy will be corresponding to the Q value of the reaction. So to keep in mind that there will be continuous spectrum for beta emission, maximum number of beta particle will have energy that will be E naught by 3, where E naught is the maximum possible energy, and this maximum energy will be nothing but the Q value of nuclear reaction. So first we'll calculate that Q value of this reaction and we'll equate to this, and we'll use this formula to calculate the Q value of original interaction. This is the important thing actually. So if you calculate that Q value, this is your equation, so I'll use Q on, that will be how much? So you know the Q value can be defined as nuclear mass of reactant minus product. So I can represent like nuclear mass of reactant minus product. And you can convert that nuclear mass into atomic mass just by subtracting the mass of an electron. So if you convert this nuclear mass into atomic mass, so I can basically represent like atomic mass of zinc minus 30 times mass of electron. So basically, you can convert that nuclear mass into atomic mass just by subtracting Z times mass of electron. Okay, so this is the nuclear mass of reactant. Now, you have to subtract that nuclear mass of products, and similarly, you can convert this nuclear mass into atomic mass. If you do this, you will have mass of a copper minus 29 times Me, and then you have to add this mass of a positron because you are subtracting. You have a minus sign here, it means basically you are subtracting. So nuclear mass of reactant minus mass of product. This side minus mass of the product, and you know that neutrino is massless. So this will be like this into c square, and this value is provided as 2.4 mega electron volt. Now you can see from here, if you will simplify it, basically you will obtain that mass of a zinc atom minus mass of a copper atom, and then you have this is minus 28 Me, and this side you have a minus 30 Me, right? So this will be like minus 2 times Me, and this value is provided as 2.4 mega electron volt. Now the question they ask to calculate Q value of this original interaction, so I'll basically use this formula to calculate the Q value, and that is our goal actually. So if you do this, how will calculate? Again, I'll use same formula. So Q value of original interaction, that is Q2 I'm taking. So that can be represented as mass of reactant. So if you do this, so I can represent like atomic mass of copper minus 29 times mass of electron. And then you have a mass of a proton on the left hand side. So you have to add this. And then you have to subtract the mass of the product. That can be represented as mass of a zinc atom minus 30 times mass of an electron. And then mass of a neutron into C square. Right? And if you do this, what will you have? You'll have first mass of a zinc atom, then minus mass of a copper atom. And then you can see here, you'll have a mass of a, if you merge the mass of electron, so you'll have plus Me, mass of electron plus Me is there. Now what will do, you know that you'll have that factor like minus, if I do like this, minus 2 times mass of electron, then actually what you are doing, this because why I am doing, because this value I know, and you have a only the mass of a plus mass of electron. Actually you are adding on mass of electron, you can see, because this is minus plus 30 Me, and here you have a minus 29 Me. So you have a plus Me. This is like plus Me, but I am adding 2 Me. It means I have to subtract minus Me, and then you have remaining part, that is mass of a proton plus mass of a neutron. So nothing is there. Logic is like that. You have to make the equation like this, because you know the value of this, that is minus 2.4 MeV. So this can be written as like this, and then you can write like this, or you can basically write like this. And I'll substitute that values now. So you know this value, that is minus 2.4 mega electron volt, and then you have 0.5 mega electron volt, and then you have 938 mega electron volt, and then you have minus 939.5 mega electron volt. Okay, just I have substituted with that values, because everything here will get MeV per C square, and C square will be cancelled. And this value, this M into C square, that is actually, you know, that is minus 2.4 MeV. So if you sum them now, you'll obtain that will be minus 4.4 mega electron volt. So this will be the Q value carried out by this original nuclear reaction. Okay. So thank you very much.